All right, so we're gonna figure out, like, let's say you want to know what this value is here, right? And constant composition means the ratios are always the same. Yeah? So if it's 2.85, and then you can go like this. There's a couple of ways you can do this. It's 1.82 grams of nitrogen for every, let's see, 1.03 grams of oxygen. Or you could say, there's a lot of, like I said, there's a lot of ways to do it. But this one, actually, you have to solve it like this. Oh, you know what? Hang on. Forget that. We'll do it like this. I like this one. You'll like this better. There's less math involved. So what am I looking for? Nitrogen, right? I'm going to try to do this one here. Right. So I'm going to say X grams of nitrogen. Okay. Divided by 4.55 grams is equal to 2.85 grams of the substance. Even though this, like, forget whatever that formula is, because that's just like, doesn't matter. So for every 1.82 grams, yeah, so I did that wrong. 4.55, gosh, sorry. 2. Nope.
I don't feel bad for struggling.
Yeah, I'm just doing that. I'm doing the ratio wrong. I would normally just do something a little different, but I think this will be easier. There we go. So this is the compound. But yeah, I mean, if you struggle, it's okay. Just as long as you figure your way out through it, right? This is compound, right? This is nitrogen. So this is what I'm looking for. So constant composition just says the ratios are always the same. So it could be the ratio of the element or the element to the compound. Okay. So then the reason I set it up this way is because now all I have to do is multiply across by 4.55. And so then I'll say that X grams of nitrogen equals 4.55 grams, like this, times, and then 1.82 grams over 2.85 grams, like this. And you can do that with, as long as you're given 2 of any of them, you can figure it out, right? So you have 2 of one sample. That's this sample here. You have all the information you need from that sample there. Then you can figure out, and so like for these two, right? If I want to know what this value is, then what I'm going to do is, so you can do the calculation later, but I'm going to say I want X, this is going to be my X again. X grams of, and it's nitrogen, for every 1.35 grams of oxygen is equal to, right? And then I go back up to this top line and I just read the values off. It's 1.82 grams of nitrogen for every 1.03 grams of oxygen. Again, constant composition just says the ratios have to be the same. And so then you multiply across by the 1.35. Originally, when I was going to do it, the X was going to be on the bottom, and I realized nobody wants to do that. Because then you have to do more manipulations. Does that make sense? Now, is that what you did?
No, I did like 20 things and got the wrong answer.
Okay. Now, I would not be surprised if when you go to the back of the book, it gives you the wrong answer because they said it's they say dinitrogen monoxide, so that's correct. Yeah. But I wouldn't be surprised like if you found wrong answers because the way they write these books is they have to have a certain percentage of the questions be different, right? And so what they do is they'll change the number. And then they have to rewrite the key, and they retypeset it every time they do that. So when they retypeset it, they introduce a whole new series of mistakes, which then somebody has to go through and fix. this. I wrote one of these one time, like a solutions manual for a book. And then I found out like every time when we went to the new edition, I found out they retypeset the whole thing. So I had to go through and find all the mistakes that they made. And I'm like, no, I'm not doing that. And yeah, they'll add a question and shift a whole bunch and they'll count those as changes to the book, which is why there's this uproar right now trying to get free books for students. You guys know about that? It's coming. Right? Anyways, and that's why I have like old editions for all my classes. You can use old editions and you can work from the older ones. Yeah. Anyways, you want to see another one of those? Set up the ratio. Okay, so this is what I want you to do. We're going to do D. Okay, I want you to set up the ratio to solve for this mass here. Because that's one we haven't done yet. How are you going to set the ratio up? Try it. Get it wrong. It's okay. There's one thing to look at it and say, oh, I don't know how to do it, but try doing it and you'll understand it. Yes. This is not a quiz.
My brain is not.
See? I see.
No,
Me either.
Andres.
No. 40 something patients today. Like 32 yesterday.
Here. Both yours. Luis.
So when I got home, I don't know what kind of
See that
I
all the light on
was,
this shit,
but I got home
especially on
and I
these
sat on
ones.
the couch and I was like, I can relax. And I was like, oh wait, I have Chem.
There's
no relaxing.
24/7. Like this, I all get them.
What did you get?
33.
Like I said, I'll try to find
It was
those. I don't know
2.5
what this is.
actually.
All right, you get your ratio set up. Like I said, you can do the math part. I just want to make sure you can get it set up, and then you can it's just plug it into a calculator. Then. Okay, so that's the ratio that I'm going to start with. There's the 1.11 grams at the bottom of nitrogen, and then the mass of the N2O at the top. So the ratio, like proportions, right? You learned this. This would be 2.85. Oops, that's a 5. The brain wants to make it an 8. 2.85 grams of N2O and 1.82. Is that what you did? So this is to this is a this is to this one. I don't know how you say ratios in math. It's the ratio. Make sure they're the same. And then you'll cross multiply it by the 1.11. Get it across and cancel it on this side. And that'll be your answer, whatever the math says it is. Are you okay with me saying just do the math
No.
on this one?
I'm so probably because it's too early.
Okay, but solve it for X. If you can't do it, see me after and we'll work it out. Okay. But yeah, the hard part of the problem is really just figuring out the setup, right? And constant composition means, it's also called definite proportion, is to find the proportions, and they will be the same in the same substance. Whenever you have a sample of a substance, that proportions, regardless of where the sample comes from, will be the same. So this is a proportion of grams of N2O to grams of N, grams of N2O to grams of N. Okay. Any other questions? Homework? No? All right. So that'll be in the notes, actually. It's recorded in the lecture. It's in the middle of the notes right now. I'm going to use the bottom half of this up here. And a quick review. So, H2O. So we have formula types. There's two kinds. There's molecular formulas and empirical formulas. What's an empirical formula? Anybody remember? And a molecular.
Is it empirical?
Yeah, empirical is the most simplified, like looking at the numbers, it's the most simplified version of the formula, okay? So for this one, right, the most simplified version is itself. It's both an empirical formula and molecular formula. Because we know the water molecule, its formula is H2O. Okay? But you only know that because you know water's molecular formula. I mean, that's been burned into your head like it's in advertising. It's all kinds of places. If you see H2O2, all right, that can't be an empirical formula because it's not the most simplified version. An empirical formula for that looks like this. Because what I did is I divided these by 2. All right. The ratio, and this is the definite, kind of like the definite proportions things, the ratio of hydrogen to oxygen is always the same, regardless of how you write the formula. Like if it's H2O2, the ratio of hydrogen and oxygen is the same as H and O. So this is the empirical formula. This happens to be the molecular formula. Okay. What about P2O4? It would be PO2 because I can divide both sides by both of those numbers by 2, right? So then the empirical formula for that would be PO2. That's the empirical. So this would probably be the molecular formula. So what we're going to do is see how to find both the empirical and molecular formula from data, like from experimental numbers, okay? And I'll try to explain it like this. What we do is we do what's called elemental analysis. And what we do is we figure out what the mass of each element in a compound is. So I'll give you an example. It looks like this. This is actually a problem from the book in the 5th edition. I just copied it over. And it says, go to the top. I think that's a compound containing selenium and fluorine is decomposed in the laboratory and produces 2.231 grams of selenium and 3.221 grams of fluorine. Just calculate the empirical formula. I might have showed you a little bit. That's the basic question. Okay. Now, in the formula, what you need to know is the ratio of the atoms in the formula. Like how many fluorine atoms are there for every selenium atom? But if you remember what we talked about last time, each element has a different mass. And so if you want to compare the number of elements, right? Each element in a formula, what you have to do first is convert it over to moles. Moles is related to the number of that atom. So the process is going to look like this. I'm going to take grams of each substance, and then the table is how I set it up. And if you do it that way every time, it should work every time. You take grams of selenium, take grams of fluorine, right? And then we're going to do this. We're going to convert that into moles. And the process for that every time is to use the molar mass of that element. The molar mass, I'll write that here. Again, reviewing, it's just the mass off the periodic table. That's how much it weighs is in atomic mass units, but that's also how many grams 1 mole weighs. That's one of the things we talked about. So we'll use the molar mass to calculate moles of selenium and then moles of fluorine. Now, if we want the atom ratio, right, what a lot of people feel like they have to do, and I'm just going to tell you, and it still works, but you don't have to do it, and I'll explain it to you, is they want to go to atoms of selenium and atoms of fluorine. And then from those two numbers, you can get the ratio, because you know the atoms of one kind of element and you know the atoms of another kind of element. To get the ratio, like the empirical formula ratio, you just divide, and that'll tell you the ratio. And so to do this calculation, you guys remember what that number is called? Avogadro's number, yeah. I really have to get that. There's a chemistry instructor I told you. She has it tattooed on her arm. I have to get her picture of her. Yeah, it's crazy. She's at City. She's like one of the young new hires. Because like old guys don't get tattoos like that. I don't. They're actually going to say something else. Now here's the thing. Avogadro's number is the same regardless of whether or not it's fluorine or selenium, right? So whatever I do, if I convert over to atoms, right, and then I end up dividing, all that Avogadro's number stuff will cancel out. Like I don't actually have to go over to atoms. I only have to go over to moles of atoms. It's like saying I have 3 dozen donuts, right? I could really turn that into 36. I could do the math, like 12 to a dozen. That's like Avogadro's number. Or I could just divide the dozens out. And so by dividing out moles, it allows me to save that step of converting it over to atoms. Now, if you do that, it'll still work. It's just more work. Okay. So this is the process. So this is the grams of selenium. I want to convert it over to moles. And so I look up selenium on the periodic table, and somebody can read that to me with 4 6. 78.96 grams for every 1 mole of Se. And for fluorine with 4 sig figs, it's 19, right? So it's 19 grams. Like that. So dividing by the molar mass essentially gives me the number of moles. So I can calculate that out real quick. So I'm going to say 2.231 divided by 78.96 gives me this little tiny number, but this is the number, 0.02825. So I'll put 48, but it's only 4 sig figs, so I'll stop it there. And that's in moles of Se. And I'll do the same thing for fluorine, 3.221 divided by 19. And I get 0.1695 26. And that's moles of fluorine. So now to convert it over to a formula, we want to get the ratio of atoms of one type versus the other. And so you end up doing a division to get the ratio. And what we technically always say is divide by the smallest. And the reason you divide by the smallest is because it gives you whole numbers, or numbers that can easily be converted into whole numbers. So I'll go divide by smallest. Which one's the smallest? Top one, right? So 0.028259 divided by 0.02859 equals 1, right? And then for the fluorine, I'm going to take 0.169526 and divide by 0.02859. And you're going to get a number. Go ahead and do that. Tell me what you get. Right, this is the moles of fluorine. Need to leave a little bit more space here, and moles of selenium. There's another box set to the right in case we need to do something else. We don't need to do it in this problem. What'd you get? Yeah, so you got 6, right? This comes out to be 5.999. So that's approximately 6. So what does that tell me the ratio is? It's 6 to 1. 6 fluorines for every selenium. So I could say there's 1 selenium and 6 fluorines. So the formula, when you write it, okay, is just going to be SEF6. That's the empirical formula for that. Okay. Now sometimes it doesn't come out to a whole number, but it comes out to like a fraction, but you have to figure out what that fraction means in terms of whole numbers. Like you have to multiply it. I'll show you that one too. Okay. Why did I divide by the smallest? Because you could have done it. It actually works either way. What if you divide by the largest? Then you end with a fraction, right? You have to be able to recognize 1/6 as a fraction. So basically, people always divide by the smallest so they get a whole number, okay? Or something that's interpretable as a whole number. Okay, let's do another one. So it says, this is for naproxen, and then I have a couple of other practice ones in the back. And then a lot of times the composition information is given as a percent. It's a percent by weight. By mass, let's say mass. Percent by mass, okay? So I have 3 elements. I'm going to go ahead and write them down here. C, H, and O. And for the grams, what I'm going to do is this. I'm going to assume that I have 100 grams of naproxen. So I'm going to assume I have 100 grams of it, right? If I have 100 grams, so a 100 gram sample, how many grams of carbon would there be? Well, if it's 73.03% per 100 of carbon, then it's 73.03 grams of carbon. I'm going to shove it all the way to the left here. Okay. And then how much hydrogen would I have? Yeah, 6.13. And then for the oxygen, I have 20.84. And this would be grams of oxygen. So same process, I need to get over to moles, and then I need to look at the ratios of numbers, okay? And again, I'll end up dividing by the smallest. So go ahead and calculate the moles. I'm gonna do it, and then I'll fill in the work before I print these notes out. But I want you to go ahead and figure out the numbers of moles and show your work in the little tiny box space that I gave you. Try to squeeze it all in there. I'm going to be writing numbers in here, and then I'll write out the work. So see if you can get this number. Yeah, that'll get you, every time you divide, do that, you get to the goal. Okay, so the setup, I'll show you the first one. Basically is, if this is 12.01 grams for every 1 mole carbon, like that. And that'll give you that number. So I went ahead and I did that all the way down, divided by the molar mass of the element. So now I have the moles, and I have to do the ratio. So which one do I divide by?
The oxygen.
Yeah, the 1.3025, right? So I'm going to take 6.081, okay, and then divide by 1.3025. This is moles of carbon to moles of oxygen. That. I'm going to get this number.
4.668.
Yeah, 4.668. Not a whole number. So we're going to have to fix it, and I'll show you how to do it in a second. Because it's not easy for a lot of people to do this, so I'll show you the easiest way to do it. Okay. What does the next one come out to?
4.7.
I think I got 4.668 again, actually. Same number?
Yeah.
Yeah, 4.668.
No. I went to the top number.
And this becomes 1, right? Okay, 4.668 is related to a whole number. Now, you can't write a formula. You can't write this. You can't go C 4.668 H 4.668 and O1, because it has to be whole numbers of atoms. I mean, they're atoms. They're the smallest things. They have to make those into whole numbers. So this is what you have to do, is you have to figure out what to multiply 4.668 by, the smallest whole number, to get it to a whole number. So 4.668, if I multiply that by 2, right, and I'll just show you this. 4.668, and I go times 2. So this is what I'm multiplying by, okay? What's that going to be? Is that a whole number? No. So, but you do this. Dot, dot, dot. Okay, so I'm going to do it by 3.
14.004.
Yeah, 14.004. That's it. So then I have to take everything and multiply by 3. So now what I have is I have this formula. I got to do times 3. The whole thing. So then it becomes, right, C 14 H 14, because remember those ratios were the same. And then O, what's O going to be? 3, yeah. A lot of times people forget to put the 3 there because you didn't really do anything with it in the first place. You just wrote 1, right? And they'll just forget. But everything has to be multiplied up. So that's the empirical formula for the process. It's also, remember, it's also the molecular formula, but the only way I know that is because I've seen it before. It's not that big. So. Okay. So how do we know? So that process makes sense. And I have a couple more. I'll have you guys try Tylenol or pineapple oil. I don't know. We'll do one of them. Those are just stolen from the homework, by the way. So I just pulled them out. I think they're the ones from the homework. I just pulled them out of that. How do you figure out? Oops, I didn't mean to do that. How do you figure out what the molecular formula is? And it works like this. To figure out the molecular formula, you have to know what its mass is. You have to know how heavy it is. So here's an example, right? I have, this is an empirical formula, which you may have figured out using the process that we just did. You get the grams or the percents, and you figure out what the moles are, and then you get the mole ratios. So this is my empirical formula. And then O. What I'm going to do is I'm going to figure out its mass. So I'm going to take 2 times 12.0, or actually you will, because I'm not going to do it. Atomic mass units plus 3 times 1.008, that's the one in your book, plus 16. Okay, so add that up and tell me what you get. Got 43. Made my head hurt though. Got 43. Plug it in. Okay. What I get is 43.054. Is that what you get? No, dang it. 004. All right. There we go. I had too many. I was carrying a too many. Try to do it in my head. This is atomic mass units. Okay. So that's how much that formula weighs. Okay, that's the mass of that formula. So we call it the formula weight. Old school. New people, young people call it formula mass. You're probably in that category. You should probably use the word mass. I'm old enough I can get away with saying weight. But it says right in the problem, right? If the molar mass of a compound is this and its empirical formula is this, what's its molecular formula? Well, what's the relationship between the 43 and the 86? So again, we're going to do a ratio and figure out what that relationship is. So what we're going to do is we're going to say, I'm going to call it this value n, because your book likes to use the number, the letter n. I'm going to take 86, and let me write out what I'm doing. I'm going to take the molecular weight, and I'm going to divide by the formula weight. And that tells me how many times that empirical formula needs to be multiplied to get to the molecular formula. So I have 86.09 divided by 43.044, which I am going to assume is like 2.00.
Yes, 2.00.
So that's my ratio, right? Now you notice I didn't care about the units because grams per mole gives me the same number as the molecular weight, the atomic mass unit, so I just left it off. So that's my ratio. I know probably people may kill me over that someday, but that's okay. So I know C2H3O needs to be multiplied by 2, so I get C4H6O2, like that. And that would be its molecular formula. If you calculate the formula weight for that, it'll be 86.09. Okay. So that's the process people go through, like when they want to figure out what the formula of a compound is, they figure out what the percentage of each element is, and then it turns out there's like a dozen techniques to figure out how much something weighs. And now it's really easy. Like we use something called a mass spectrometer, and you just throw it in there and it tells you what it weighs. It weighs molecules. Yeah, not the traditional way, but that's what it does. Oh, almost used enough time. You guys want to do A or B? A? A sounds good to me. Go ahead, do it. What? Okay, I'll start you. What do you need to have? Make a table, right? And you're going to have the elements. So I'm just going to make a line and say C, and another line and say H, and another line, say N. That's the one I was hoping you'd take because it has more elements in it. Another line, and you do O. And then you're going to do grams, moles, and then the ratio. Yeah, we'll do it like that, gram moles ratio. We'll call it RAT. And I'll fill in this table and I'll let you figure it out. I'll leave that line out. We'll just try to work underneath. So that's how it starts. Go ahead, work out. If you have questions, just raise your hand and I'll. So what you guys got?
Mhm.
Yay, we can do it. All right. Do you need to do anything else after that other than write the formula? I haven't written the formula yet, but we'll write the formula. No? Yeah, just write formula then. Because that's the answer is what's the empirical formula usually. So, or the question is, so C8, H9, N1, O2. And then the 1 you don't have to write, but I just have it. But it's there. Okay, so that's all we have for this chapter. If you have questions, it's a long weekend, so there's no Monday office hours, but I'll be around. I'm actually going to be around on Sunday, so if anybody wants to check in, just text me, 2 o'clock. I'll actually be here. I have a hybrid class. I have 4 different classes I'm teaching. That's why I'm juggling lots of paper. And I told them their first exam would be on this weekend because I was hoping that they didn't have to work on a holiday weekend. Still some of them have to, because that's the way life is. So I'll be here on Sunday at 2 o'clock. So if you want to just come in person and get help, I'll be here. So we got a lab. I'm going to give you a 20-minute break before lab for a couple of reasons. But you need to go. Do you have the lab printed out? Did you guys do the pre-lab? Did you turn in your nomenclature worksheets in the pile? Let's get all this done.
Do I start it early?
Huh?
If we want to start the lab early, can we start it early?
No, actually, we can't because there's another class with the exact same materials. That's why I'm lecturing today a little bit. Yeah, and then turn in your pre-lab in a separate pile. But the nomenclature worksheet can be one pile together. These I'll get back to on Tuesday. And there were a couple of things that people didn't pick up before, so they're in this pile that's next door. I'm going to get a folder system going for this class because there's lots of things.
Huh?
No, you just
Look at this page. Crazy. Maybe I can do
No.
some of it.
So you're going to do this homework and put that in with it. It's like wherever I stop. Yeah, that's fine.
Like the back.
Stapler? Yes, I do. How many atoms? Oh well, let's do it up here if you need help. Yeah, she said she needs help on the pre-lab, so I'm going to go over some of that then. That's fine.
I was struggling.
So I'll leave the recording going, actually. I'm just gonna open up another document. Let's see, where'd it go? There it is. And then we're going to do the mole. Oops, I want that. The mole. Mole. I'm gonna open it with. Yeah, don't ask me to print it because you know what it looks like when I print it. Oh, it's horrible, yeah.
And that's already full. Or we just need to know that. What I mean?
Post-lab, pre-lab, okay, there we are. And I gotta make sure I share this. Share the mole. All right, which one? Questions?
Number
4 and 5. Ah, yes. So how many atoms of zinc are in 10.0 grams of zinc iodide? So this is what you gotta do. You have to figure out what the mass of zinc iodide is first, okay? So zinc iodide. Yeah. So it's zinc, right? Plus 2 times iodide. And you said you got what? 319.3? 35? And that's grams per mole or atomic mass units either way, right? So now, I have 10. So I want atoms of zinc. And I've given 10.0 grams of zinc iodide. So let me write the process. Let me write the process that you use for these like every time, okay? You're gonna go from grams to moles of zinc iodide. And then you're gonna go to moles of zinc. Now there's 2 ways to do this, but this is the way that I usually tell people because it kind of makes more sense. And then you're going to go to atoms. And when I do atoms of zinc, I just don't write atoms. I just do zinc. I don't put moles. I don't put anything with it. I just say ZN. Okay, but just that's when you see that in the answer. That's what that's going to mean. Oh, do you do railroad tracks or do you do? All right, I'm gonna do railroad tracks, just to make you happy. So I need 1, 2, there's 3 conversions, so there's my first one. And then you say it's 319.35 grams of ZNI, right? 2 for every 1 mole of ZNI2. So that's the first step. Second step is this, right? It's the conversion of zinc moles, zinc iodide moles to moles of just zinc. So how many zincs are in the formula? Yeah, so this is what you write. You write 1 mole of zinc. Now, if there had been 2, you'd have put 2 there, right? For every 1 mole of ZNI2. So what's happening now, get this thing out of the way, is we're canceling out units like this. And the last step, the third part of the process, oops, didn't want to do that. It's not that exciting. The third part, the last bit, is to go like this, 6.022 times 10 to the 23rd. Zn, right, those are atoms, for every 1 mole of Zn. And that cancels that. So in step number 2, that's formula ratio. That's what that's called. And all ratio. It's when you look at the formula, it's just a number of those things in the formula. So it had been 2, you'd have put 2, and 3, put 3. It's the same. The analogy would be like I did in the classroom the other day. You wanted to know how many arms were in the classroom. You don't count every arm. You count the heads, and then you use the formula ratio. It's 2 arms for every head. Right? You could count other body parts. It doesn't really matter, but it's 2 to 1. And then to get to atoms, that's step number 3. That's always Avogadro's number. Okay.
And for the answer, do we write it like Avogadro?
Yeah, in scientific notation. Yeah, right. It's not, because it's going to have so many zeros after it if you don't. It'd be like a number, and then there'd be probably 21 zeros at the end. Yeah, it'd be painful. Okay, so go ahead and do 5 that way. You're gonna. Did you do the molar mass of K2SO4?
Yeah, 175.2.
So try to follow that process, right? You have 25 grams of that. You want to get it into moles, and then you're gonna use the formula ratio. It's gonna be 2 to 1 now because there's 2 potassiums in the formula. Okay. Then I'll set it up, and then you guys can run the math, and then I'll check back. We'll check back in a second. We'll see what people got for number 4. But go ahead and try that last one. Sorry. The syllabus says like what we're doing each week. The modules just say these are the labs for that module, and I try to have them in order. Even numerically, they're not in order because they come from the lab book. Actually, Miss Cornell's book, and she just gives it to her students for free. Yeah. Well, that's why I said Tuesday. I said, read the formula set. Read it. You know, in class, you don't understand it. You'll see it. You'll go like, oh, that's. Yeah. It makes a lot more sense if you look. It's a good habit too. Yeah.
I
At least the post. Oh, yeah, so you add all that up, right?
Wouldn't you, yeah, but wouldn't you just put it into this formula in a sense? Because
She's doing different problem.
this is, yeah, well, I'm doing two too. So this is the amines, all
Yeah.
this.
So if you wanted to show one, what mass would you weigh out? It's this number. Because that's, yeah, the number, that's
But
the,
then this, it says in
how many moles
100
are?
grams.
Oh,
When you
yeah.
set it up like this, the fact that you go across and turn across,
Yeah.
use
So,
the amines at the bottom.
yeah, and then that's it. You're done
But this
because,
only said oxygen. This one says 100 grams of the whole.
oh, how many moles? Oh, yeah, but this one, yeah, so you just want to know the whole thing. You're done at that point there. You just stop. Because it'll be moles of your cup. It'll be moles of that. Okay?
Yeah, so we wouldn't. Okay.
You don't need that next.
That's what I was thinking. Yeah, so this one specifically because I was using this formula to kind of figure out.
If you're really good at doing like molar mass and you're tired of doing molar mass, I can tell you a way to cheat to do it for homework.
This
Not
one
on
here
exams.
is-
But I'm not going to tell the whole class because some people are still figuring it out. If you're like, oh yeah, I'm going to do that every time you're getting it, I have this cool app that I can show you.
But this one.
Yeah. Okay, so what was the
Did you get 100? Started like this. Yeah.
You just like putting, why do I draw
100
this? Probably really long, so it's dividing by the number you won't remember. That's
And then
that's.
1 minute.
I'm gonna set this one up now.
Over the amines. Yeah. So that's how you're talking.
All right. So let me set this one up. Oh, what did you get for number 4? No, what did you get for number 4? 10 to the how many? 20, yeah. Like that. Okay. So we're going to do the same thing for potassium in the next one. So here's the thing. It's important to use units to guide yourself through these problems. Don't just try to remember, divide this by this, divide this by this, because when it comes down to it, you just won't remember all the different steps that you have to do. Units are telling you what to do, okay? So I have 25 grams of this, right? I want atoms of potassium. And then you start with the number you're given, so 25.0 grams of K2SO4, sorry, that S is a little weird, divided by, oh, sorry, railroad track. So the first thing you want to do in these problems, just in keeping it generic, you want to get it to moles. So to get it to moles, it's 175.25 grams per mole. Okay. So I'm going to put 175.25 grams down here and then 1 mole up here, and that's K2SO4. In essence, I'm dividing by the molar mass, but I know to do that because I need to get these grams to cancel out. I want to do that in red. Sorry. Shows up better. Okay, that's what I want to do. I want to cancel units, and now I have moles. The next step, again, I'm still following this pathway that's up here. I'm still doing this, but I just substituted now potassium in there. I just changed the symbol. But I want moles of potassium now. So then you look at the formula and say, well, how many potassiums are in there? There's 2, so it's 2 moles of K for every 1 mole of K2SO4, like that. All right? And so that'll cancel out. And then the last step is to go from moles to something, the actual number, so it's always Avogadro's number. So in this last step, move this guy out of the way. It's 1 mole of potassium is 6.022 times 10 to the 23rd potassiums. And I just usually write K because you write atom every time, it just takes 2 space. But if I don't put anything else with it, that's the number of those units. And then it works out that this cancels. Okay. So anytime you're doing a calculation / conversion, right, involving a conversion factor of any kind, set it up and see the units cancel, because that tells you where the numbers are supposed to be in the calculation. Now, how do you do this on your calculator? You're going to take 25 divided by 175.25 times 2 times 6.022 times 7.3. You just go each step and you see what's the operation. You just do that next operation. Orders of operation for multiplication and division don't matter. So just do them in any order. You can multiply them all, divide them all. It's up to you. Okay, so I'll let you figure out that answer. Throw it in your calculator. Give you a second to finish working it out.